Assalamu alaikum and very good morning, everyone. This is my lecture entitled Intermolecular Forces for CHM 577. This is my lecture number 9 for this course. The slides were prepared by Dr. Amalina. I'm presenting the topic to my group of students. Yep. So for this lecture, the outline of this lecture, I'm going to be talking about van der Waals forces, hydrogen bonding, dipole-dipole interaction, ion-dipole interaction, instantaneous dipole-induced dipole interaction, and ion-induced dipole interaction. If you're wondering what they are, actually, there is a way of categorizing the interacting particles and what are the forces that exist when these particles interact. This is kind of a chart of how you're going to determine what forces are going to be present in whatever situation that you encounter. But as you go through this lecture with me, we are going to go through each one and I will explain it to you one by one. So to understand intermolecular interactions, you have to do a little bit of a recap on the properties of liquids and solids. Of course, there are 3 states in which matters exist. They can exist in the gaseous form for gases, liquid form, or solid form. And ever since you were a young chemistry student, everybody understands that gases expand to fill their container. Wherever you put the gases, they will take up the shape of that container that they are put in. Liquids will retain the volume, but they will not retain the shape. Once you take out the container, the volume will still be there, whereas gases, once you release them from any particular container, they will just expand the volume, whereas liquid will not expand the volume upon release from any container. And solids, on the other hand, if you release it from a particular container, solids will retain their volume and will retain their shape. So that is really how these 3 phases differ from each other. Properties of these matters, gases, liquids, and solids, can be understood in terms of how tightly the molecules are packed together and what is the strength of the intermolecular interaction that exists between the molecules. So if you are looking at a gaseous phase, you will see that the gases are easily compressed, expand spontaneously, they will fill the container, widely spaced molecules, a lot of empty space between them, motion of the molecules is random, and a very, very weak attraction between the molecules, practically very, very little attractions between that molecule and the other molecule. Whereas in liquid, you will see that compared to the gases, the molecules are packed a little bit tightly. There is a little bit more order. They are able to move past each other with some degree of difficulty. And the intermolecular attractive forces in liquid is stronger than the forces in gas. And when we move into solid, the molecules are tightly packed, they are highly ordered, the molecules are highly ordered. You can see there's a lot of organization in this packing of the solid. Yeah. Very strong attraction between the molecules that are holding them in place, and they are effectively locked in position. And when we talk about the gas, the liquid, and the solid, there are forces that are keeping all these molecules so that they become what they are. The forces can be intramolecular, i.e. within a molecule. Yeah, within. Intra means inside, within the molecule. And this is usually the bond between the atoms in the molecule, and it is the force that keeps molecules together, the bonds. But there are also intermolecular forces, the forces that exist between the molecules. Yeah, these dotted lines. The dotted line is an example of intermolecular force. Uh, they are attractive forces between the molecules, and they are responsible for keeping matter in either the solid or the liquid phase. Whereas the intramolecular forces really will not influence whether that particular molecule is going to exist in solid, liquid, or gaseous phase, whereas the intermolecular forces determine. However, the intramolecular forces, or the bonds within the molecule, are always stronger than the forces between the molecules, or intermolecular forces. That is understood. For example, if you have hydrochloric acid, HCl, the intramolecular forces is actually the bond, the covalent bond that exists between hydrogen and chlorine. That's the intramolecular force. But between one molecule of HCl to another molecule of HCl, there is an attractive force between the hydrogen of one molecule to the chlorine of another molecule, and that is called a weak intermolecular attraction. So, a strong intramolecular attraction between H and Cl, and this control the chemical properties of the HCl, whereas the weaker intermolecular attraction exists between neighboring HCl molecules, and they determine the physical property of this substance. So intramolecular attraction determine chemical properties, whereas intermolecular forces or attraction determines the physical properties. Now, when we talk about intermolecular forces, they are again generally weaker than the covalent and ionic bonds. The covalent and ionic bonds are usually what's found within or intramolecule. Less energy is required to vaporize a liquid or melt a solid. Boiling points can be used to reflect the strength of intermolecular forces. The higher the boiling point, the stronger the forces. And there are many types of intermolecular forces. You have intermolecular forces called the London forces, the dipole-dipole forces, ion-dipole interaction, and hydrogen bonding. That is intermolecular. Whereas within the molecule or in the chemical bond, you have ionic or covalent bond. So the London forces are really, really very, very weak forces. Only between 1 to 10 kilojoule per mole of energy is needed to break that London forces. And when we talk about dipole is also another weaker attractive force between molecules, 3 to 4 kilojoule. Ion dipole, 5 to 50 kilojoules. Hydrogen bonding is a little bit more significant. 10 to 40 kilojoule is quite strong compared to the others, yes. But the chemical bonding, the ionic bond, can have a strength of between 100 to 1,000 kilojoule per mole, similarly with covalent bonds. Okay. When you have a situation where you have particles interacting with one another or molecules interacting with one another. When we talk about molecule, we are talking about either polar or non-polar molecules. And the extreme side of that would be ionic compounds. So ionic compound does not have any polarity. They simply become ions, positively charged and negatively charged. So if you can recall, ionic compounds are not polar. They are simply dissociating the anion and the cations. Whereas the covalent compounds, they can either be polar or non-polar. That we have learned in the previous lecture that I have given you, where you determine the polarity of the bond and then the polarity of the molecule depending on the dipole moment, combination of dipole moments within the molecule. Now, when we talk about molecules, which can be polar or non-polar, there are two big division between the forces that act between those molecules. When the molecule has hydrogen and also has nitrogen, oxygen, or fluorine, N, O, and F, now it is very, very much likely that you are going to encounter hydrogen bond. Now, hydrogen bond is the strongest intermolecular forces that you can find. Hydrogen bond, that means the hydrogen. I'm going to go through hydrogen bonds with you later. I'm sure you have probably encountered hydrogen bonds before, but I'm going to go through it anyway with you. Is hydrogen in the presence of three very, very electronegative atoms, which are nitrogen, oxygen, and fluorine. So fluorine is the most electronegative element, highest Pauling value, followed by oxygen and followed by nitrogen. So these three, when they are present in the situation where there is hydrogen, then you will probably encounter hydrogen bonding. And for a situation where there are no nitrogen, oxygen, or fluorine, you are simply going to encounter intermolecular forces that is known as the van der Waals forces. Now this van der Waals forces can be divided roughly into three. You can have ion-dipole interaction. This is when you have ions in the presence of polar molecule. For example, sodium chloride in water. You know water is a polar molecule. So sodium chloride in water will have interaction between ion and the dipole of that polar molecule that is your water in this example that I've given you. Now, there is another type of van der Waals forces that you might encounter, which is called the Dipole-Dipole forces. Now, when you talk about dipole and dipole, what comes to mind? What comes to mind are polar molecules. Yeah, polar molecules, when they interact with one another in a container, neutral polar molecule, that is, molecules will always be neutral. Then neutral polar molecules interacting with one another will produce dipole-dipole forces, whereas the third type of van der Waals forces is called the London dispersion forces. Now, London dispersion forces will become very, very important or very significant when the molecules, either polar molecules or non-polar molecules, when they are close with each other or when they are within proximity of one another. That means when the molecules come close to one another, London dispersion forces will be created. And this London dispersion forces also in turn has three different types. Okay, and The first type is called the instantaneous dipole-induced dipole interaction. Now, when we talk about induced dipole, that means initially that molecule is not polar. Initially, it is not polar. So we're talking about non-polar molecules that when they become close to one another, they will have a movement of electrons within those molecules that will spontaneously or instantaneously create temporary dipoles. So if you can imagine a bus moving where it is packed full of passengers, and the passengers are seated well balanced. Everybody is sitting nicely on a bus, and the bus is moving slowly, so the passengers are not shaken, or they're sitting nicely. But when the bus moves very fast, you will see that passengers will start to sway to the right or to sway to the left, and swaying of the passengers within the bus will create weight on one side of the bus or the other side of the bus. So similar with these non-polar molecules. When the molecules are moving very fast, the electrons are going to be shaken a little bit, are going to be displaced a little bit, creating a temporary dipole. Now, when a temporary dipole is created within a non-polar molecule, it will give effect to the next neighboring non-polar molecule. It will induce some kind of polarity within the neighboring molecule. So you have instantaneous dipole. Now that means the dipole that exists instantaneously through the fast moving, and then that dipole that is instantaneously created within a non-polar molecule will affect the next or the neighboring non-polar molecule, making an induced dipole. So it is the interaction between your instantaneously produced dipole with the induced dipole that existing between two non-polar molecules. So this kind of London dispersion forces is called the instantaneous dipole-induced dipole interaction, and will only occur for non-polar molecules only. Now, the second type of, now as you can imagine, these are very, very temporary, very, very transient, and obviously those forces are quite small. Yeah, London dispersion forces are quite small. Now, the second type of London forces is dipole. Now, when you talk about dipole, it is always polar molecule, like water or ammonia. Ammonia is a polar molecule. Now, when you have a polar molecule sitting next to a non-polar molecule, that polarity will create an induced dipole, just like that instantaneous dipole that I was talking to you about before. So any non-polar molecule will have induced dipole. So you must remember, when in chemistry, when we talk about dipole, it is always about polar molecule. When we talk about induced dipole, it is always about non-polar molecule. So when you have polar and non-polar molecules interacting with one another, then you have this second type of London dispersion forces. Right, and the third type of London dispersion forces is ion-induced dipole interaction. Now, look at that interaction. Ion, obviously, you're going to have an ion. What about induced dipole? Who can experience induced dipole? Induced dipole is always happening to non-polar molecule, not polar. Yeah? Polar will always be dipole. So when you have ion-induced dipole interaction, it is always between one ion, either a positively charged ion, a negatively charged ion with any non-polar molecule. For example, if you have methane. Now, methane is a non-polar molecule. When you put, for example, sodium chloride in methane, you probably will get this ion-induced dipole interaction. Yeah. So I have some notes here. An ion dipole force, attractive force between ion and polar molecule. There you go. Dipole-dipole is between neutral polar molecule, and London dispersion forces are only significant when molecules, either polar or non-polar, are close to one another. Right. Now let's talk about this hydrogen bond. Can you recall hydrogen bond here? Can you see this? Hydrogen bond will only occur. It is a special dipole-dipole interaction between hydrogen atom in a polar NH, OH, or FH bond and an electronegative oxygen, nitrogen, or fluorine atom. So either A bonded to H, and then there is a B, where A and B can be either N, nitrogen, oxygen, or fluorine, or you can also have A bonded to hydrogen, and then you have another hydrogen, another A, either nitrogen, oxygen, or fluorine, from the neighboring molecule. So if we look at the bond of hydrogen and fluorine, if you recall the Pauling's electronegativity value, hydrogen is 2.1 Pauling electronegativity value, whereas fluorine is 4. The difference between the electronegativity value is 1.9. It's really quite high. So the difference is 1.9, and you definitely know from that value that HF is a polar bond. Yeah. And on a similar explanation, the delta En of hydrogen and oxygen is 1.4, slightly smaller than HF, but it is still a polar bond. And HN is also another polar bond with a smaller difference of electronegativity value of 0.9. The high value of difference between electronegativity of NH, OH, and HF bonds cause these interactions between them to be strong, which is sometimes up to 5 times stronger than the normal dipole-dipole forces. So when you have a situation like this, let's have a look at the next slide. Now, 2 essential requirements for the formation of a hydrogen bond. The first one must be one molecule must contain at least one hydrogen atom which is attached to a highly electronegative atom, either fluorine, oxygen, or nitrogen. And then the second condition for hydrogen bonding is that the other molecule must contain an fluorine, oxygen, or nitrogen atom that provides lone pair of electrons. Now remember, these are all elements that exist on the right-hand side of periodic table, and they have a lot of electrons, p electrons, and they will create lone pair of electrons. So if you encounter these two conditions existing together, then you are going to be having hydrogen bonding. Now, why is hydrogen bond considered a special dipole-dipole interaction? Now, let me, the arrow that is colored red, is the upward trend of boiling point, as well as the blue. Now, if you just look at the progression between methane and silicon H4 and germanium H4 and tin H4, they are going up. The boiling point of these molecules, just look at this blue one at the bottom, they increase as the molecular size of that molecule is going up. All of these molecules that are in this table, they are all polar molecules. Similarly, when you look at phosphorus, this is actually group 4, going from carbon down to silicon, germanium, and tin. And then group 3, you have nitrogen. It should be here. Nitrogen should be here, NH3, but it is way up there. pH3 is there. ASH3 is going up, SBH3. Similarly with your group 7, you have chloro, bromo, iodo, each one of them going up. The only exception is that water, HF, and NH3 or ammonia, these have unusually high boiling points. So something must have been existing in these 3 different situations where you have high boiling point. Water, HF, and NH3 all have abnormally high boiling point, unlike the methane that you observe. So you have here methane, NH3, H2O, and HF. Everything in this group 4 is fine, but going on to group 5, group 6, and group 7, things start to show a divergent or a different trend. So let me explain that to you, how it happens. Now let's have a look at ammonia. Ammonia is NH3. There is a lone pair of electrons on nitrogen. And everybody knows that ammonia is a polar molecule, and there are 3 polar bonds in ammonia. Each one of the NH bonds are polar, and the hydrogen in each of the ammonia molecule, they are delta plus. That means they are having a partial positive charge, whereas the nitrogen, they are all having a partial negative charge. So the hydrogen of one ammonia will have a strong interaction with the lone pair of the nitrogen in a neighboring ammonia. So that is an example of hydrogen bonding, where the hydrogen of one ammonia is having an attraction to the nitrogen of neighboring ammonia. Yeah, you can see that this is the situation where the hydrogen bond exists in ammonia. On average, each ammonia molecule can only form 1 hydrogen bond. Yeah, on average. Each ammonia molecule can only form 1 hydrogen bond. Why is that? Because each one ammonia has only 1 nitrogen, and that only 1 nitrogen is the only one atom that has lone pair. And lone pair of electrons are needed to form hydrogen bond. So even though you see here that 2 of these hydrogens are bonded, but the partner to which they are bonded with is just another nitrogen from ammonia on the left and another nitrogen from ammonia on the right. So it is on average that each ammonia on average has only 1 hydrogen bond. Now let's have a look at HF, which is hydrofluoric acid. Now this is one HF molecule. This is another HF molecule. So you can see here, this is a very, very polar bond. There is a delta positive on each fluorine and a delta negative on each fluorine and a delta positive on each hydrogen. And this delta positive hydrogen will interact with the lone pair of electrons on the neighboring fluorine. And similarly, it's making this kind of a zigzag pattern where each HF molecule has only one hydrogen atom and will only form one hydrogen bond. So ammonia just now, one molecule, one hydrogen bond. HF, one molecule, one hydrogen bond. Now let's have a look at water. Now water, on the other hand, will have one oxygen and two hydrogen. Each one of the oxygen has two lone pairs of electrons. You know how this is happening? Through the Lewis structure. So if you draw the Lewis structure of water, you immediately will know that there are two lone pairs of electrons on oxygen. Now, because two lone pairs of electrons on one oxygen, that particular oxygen can bond with two water molecules, one on the left and one on the right. So each water molecule has two hydrogen atoms and two lone pairs of electrons. And on average, each water molecule can form two hydrogen bonds. And that is the explanation of this situation, where you see delta, the HF has a delta which is very big, 1.9. NH has a delta of quite small, 0.9. So the fact that boiling point of HF is higher than ammonia, it is really understandable, because the higher the polarity, which is reflected through the value of delta, the stronger is the hydrogen bond that exists between the molecules. So the stronger the hydrogen bond, obviously the higher the boiling point, because you have the hydrogen bonds holding these molecules together, and it requires heat to separate or to break those hydrogen bonds to make this hydrogen bond boil, or to make it into gaseous substance. So it requires a lot more energy to boil your HF compared to your ammonia. Ammonia boils at minus 33.3. Yeah. But the situation is slightly puzzling if you look at only delta N, delta electronegative, because when you look at simply the difference between electronegativity, HF is 1.9, whereas water is 1.4. So using the same argument, HF or hydrofluoric acid should have a higher boiling point than water. However, in real life, or when people go into the lab and they measure the boiling point of water, it is a lot higher than the boiling point of HF. So what is going on? What is going on is the fact that each water molecule can make two hydrogen bonds, unlike your HF. HF can only make one hydrogen bond. So the more extensive is the network of hydrogen bond, the more difficult it is for you to separate the molecules, i.e. to boil water. Because when water is boiled, the molecules are free from one another. There are no more forces that hold the molecules. There are no more intermolecular forces. So hydrogen bonding is a lot more extensive happening in water compared to HF, despite the fact that it has lower polarity compared to HF. Yeah. So the boiling point of water is bigger than HF because water can form hydrogen bonds more extensively, regardless of the fact that HF bond is more polar than HO bond. I hope that makes sense to you. Now, this is another explanation of hydrogen bonding in water. The small size of hydrogen, along with the shape and polarity of water molecule, they all add up to a relatively strong attractive force between the two neighboring water molecules, and the hydrogen bonding is the strongest of the intermolecular forces. So each one water molecule will be bonding to at least two other water molecules, and it's a lot more difficult to break those intermolecular forces, making water having higher boiling point than the others comparatively. Okay. Going on to the next one, I have explained to you when we talk about dipole moment, it is always for polar molecule. And when we talk about induced dipole moment, it is always about non-polar molecules. So we are going to talk about London forces next, yeah? The London forces. Yep, I'm going to talk about London forces. Yep, London dispersion forces. So the first one is the ion-induced dipole interaction, which is when you have ion, yeah, attractive force that is the result of interaction between ion and a polar molecule. Why do you say polar molecule? Because we're talking about dipole force. Dipole, not induced dipole. And it is commonly found in solution, especially important for solutions of ionic compounds in polar solvent, for example, sodium chloride in water. The strength of this interaction depends on the charge of the ion, the dipole moment of the molecule. So the stronger the charge, the more it is going to interact with the molecule, and the more, the stronger it is going to be. The strength of the forces will make it possible for ionic substances to dissolve in polar solvent, because it is the interaction between the anion and the cation with the polar end of the molecule that makes that ionic molecule or ionic substance dissolve. For example, in water, you have the hydrogen to be delta positive, so it is the chlorine going to be interacting with the hydrogen, and then your sodium will be interacting with the delta negative oxygen. So when the chlorine and the sodium or sodium chloride has different ends of the molecules to deal with, then they are broken and you have your ionic compound dissolving in polar solvent. Yep, for example, this one. If we talk about water here, you have oxygen. You have your oxygen and negative. You have your hydrogen and positive, and you're going to have the positively charged sodium to interact with the negatively slightly negative end of this polar, and the iodide. We're talking about sodium iodide here. So the positive or the cations attracts the partially negative end of a neutral polar molecule, and the anion attracts the partially positive end of a neutral polar molecule, and what will exist between them is what we call the ion-dipole interaction. Yep. Ion-dipole attraction becomes stronger as either the charge on the ion increases or the magnitude of the dipole of the polar molecule increases. So if the charge, for example, you have sodium and magnesium, you are comparing between sodium and magnesium. Magnesium has a higher charge, than sodium. So magnesium will interact more strongly with water compared to sodium because of the high charge of magnesium. So magnesium 2 plus ion with higher charge and smaller size interact strongly with water. Yeah, there is a difference in the magnitude of interaction of sodium with water compared to magnesium with water, right? And ion dipole forces is where you have hydration. Hydration is an example of common ion dipole interaction. In the aqueous solution, metal ions are usually surrounded by water molecules in octahedral arrangement. So you have, for example, here chromium 3 plus. For chromium to dissolve in water, it usually will have on 6 corners each water molecule on each of these 6 corners. So that is the ion dipole forces. Now, next London forces that we're going to talk about is dipole-dipole attractive force. So dipole-dipole is between polar molecules. When you talk about dipole, is polar. For dipole is another polar. So a dipole-dipole force exists between neutral polar molecules where the partial positive charge of one molecule is near the partial negative charge of another molecule, like this example. And the molecules must be in close proximity for the dipole-dipole forces to be significant. As you can remember, London dispersion forces only become significant when the interacting particles or interacting matters are close to one another. The dipole-dipole forces are characteristically weaker than ion dipole, obviously, because ion is a stronger pull. And the dipole-dipole forces will increase with the polarity of the molecule. The larger the dipole moment, the greater the force. That is quite logical, yeah? So when you talk about dipole-dipole interaction, when we're comparing between propane, dimethyl ether, methyl chloride, acetaldehyde, acetonitrile, looking at the dipole moment, you look at the molecular weight here, okay, not quite the same, but they are of similar range. But the only difference is the dipole moment. As you can see, the higher the dipole moment, the higher the boiling point. The lower the dipole moment, the lower the boiling point. I.e., the more polar the molecule, the higher its boiling point, the more attraction, i.e. dipole-dipole attraction exists between those molecules. For polar molecules of similar mass, boiling points increase with increasing dipole, as you can see in this table or in the slide. As I told you earlier, the London dispersion forces becomes significant only when molecules are close to each other, when they are in close proximity with one another. These forces are present in all molecules, whether they are polar or non-polar. Due to electron repulsion, a temporary dipole of one atom can induce a similar dipole on a neighboring atom. For example, if you have helium, having a helium, it moves, so the electrons, the movement of electrons will create instantaneous dipole, and the instantaneous dipole will induce another dipole in the neighboring helium. So there is some kind of weak attraction between this helium and that helium, because that is a partial, tiny positive, slightly positive end. This is a partial, tiny, slightly negative end. That there is some kind of weak attraction between these ends. So that's what we call the London dispersion forces, right? The London forces or the London dispersion forces, very, very weak attraction between non-polar molecules, arise from the interaction of instantaneous dipole on the neighboring molecule that have induced dipole, and the net interactive attraction of this is attractive. So you have the London forces to be very, very quite weak, yeah? So what are temporary or instantaneous dipole and what are induced dipole? Yep. The temporary or instantaneous dipole is because of the movement of atoms together with their electrons, result in electrons gathering on one side of molecule. Remember that bus that are moving too fast, you get the passengers swaying to the left or to the right. So you have that's happening. So helium ideally will not have any dipole, but due to a gathering of electrons on one end, you're going to have a dipole moment, a temporary dipole moment for helium. And that temporary dipole moment will make the neighboring helium also having a induced dipole. Yeah. This molecule is close enough with another molecule, induce a dipole with its neighboring molecule, and due to random movement, the temporary dipole is created the next moment, and then it will be gone the next moment. Yeah, it is very, very transient, on and off, on and off. You see it and you don't. You see it and you don't. That's why it is very weak. The arrangement keeps on changing as the molecules keep on moving. So the likelihood of induced dipole depends on the polarizability of atoms or molecule. If a particular atom is easily polarizable, that means it is a big atom or it is a big molecule. The electrons are, far from the nuclei. Then you have high polarizability. So the polarizability is a measure of how easy it is for the electron cloud to be distorted, and it will increase with a larger electron cloud and a larger molar mass. Yeah, when the electron cloud is big, it is easily polarizable. When the mass is big, it is easily polarizable. So induced dipole can easily occur for large atoms or large molecules. So large electron clouds are easily deformed compared to small ones, resulting in partial charge is also larger, and the larger molecules will experience larger London forces than the smaller molecules. So as you can see here, fluorine and chlorine, yeah? Fluorine is small, chlorine is big. Fluorine has a little number of electrons, whereas chlorine has more number of electrons. So comparing between fluorine and chlorine gas, chlorine has a higher boiling point compared to fluorine. And bromine is even higher. Iodine is even higher because iodine is being bigger. It is more polarizable. It will have experienced more London forces. Yeah. Same with helium, small. Neon is big. Argon is bigger. Xenon is bigger. Radon is bigger. So as the noble gases become bigger, they become more easily polarizable. Radon is the easiest. So radon has the highest boiling point, minus 61.8 compared to minus 268.6 for helium, which is small and not very easily polarizable. So in conclusion, polarizability increases with greater number of electrons and more diffuse electron cloud. And you can see how this is. So I hope you are going to be able to explain the melting point of these non-polar molecules. How is Ci4 having higher melting point than CH4? Yeah, this is carbon with 4 iodine, this is carbon with 4 hydrogen, and how the smaller one is having very, very low melting point compared to the bigger one. Yep, explain that. You can explain that using dispersion forces that increase with the molar mass. Now, the strength of van der Waals forces depend on the size, depend on the surface area of the molecule and depends on the polarity of the molecule. The bigger the size, the stronger the van der Waals forces. The higher the surface area, the stronger the van der Waals forces. And the higher the polarity of the molecule will give you higher van der Waals forces. And in decreasing order of importance, size is very important. Size is very important compared to surface area and compared to polarity. So this is how it is. So looking at the helium, neon, and argon, these are all noble gases. Fluorine, chlorine, and bromine, these are all halogen molecules. Methane, ethane, and propane, they are all alkane, small, big, and biggest. Look at the boiling point. The higher the boiling point will signify the higher degree of van der Waals forces existing intermolecularly in those molecules. Yeah. I'm sure you can have a look at these slides and make sense of it yourself. So I'm going to let you go through this slide yourself and get the explanation yourself. What type of intermolecular forces that exist between these molecules, HBr, CH4, SO2. I have given you all these answers here. I hope you understand the answers. I'm not going to repeat myself because this lecture is going to be very long otherwise. Surface area. Now, the van der Waals forces increase with surface area, and these are the more surface area you have within that molecule, the more van der Waals forces will exist. Yeah. The molecular shape also affect the London forces. The more compact molecule will have lower London forces, obviously, because of the low surface area. When you compare neopentene, which is CH3 4 times with carbon, you have the same number of carbon between neopentene and N-pentene. You have 5 carbons and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Same, all the formula is the same. One is neopentene, which is clumped together, and another one is N-pentene, which is a long chain of carbon. Both are non-polar. They all have the same number of electrons. The space filling models is shown in here. The hydrogen atoms in the more compact neopentene cannot interact as well with the neighboring molecule as the hydrogen in the more chain-like N-pentene. So these hydrogens are not going to be interacting very well. It's going to have a lower boiling point compared to your N-pentene. Neopentene has less London forces compared to N-pentene because of the open shape of the N-pentene compared to the closed shape of your neopentene. And then polarity of molecule. For molecules with comparable molecular sizes and shape, dispersion forces are approximately equal. Then the strength of the van der Waals forces will become dependent on the molarity of that molecule. Between polar-polar molecule, the force is bigger compared to polar and non-polar. And the smallest attraction is between non-polar and non-polar. That really makes a lot of sense anyway. So when you look at acetone and ethylene glycol that has this structure, acetone, is a polar molecule and experience dipole-dipole and London forces. Ethylene glycol, which also has 10 atoms, it has, in addition to it, and in addition to the London force, it also has hydrogen bonding. As you can see here, O and H. There is oxygen and there is hydrogen. Hydrogen that is bonded to oxygen, and that is creating a possibility of hydrogen bonding. So therefore, the boiling point of ethylene glycol is a lot higher than acetone because of the presence of the hydrogen bonding. O and H here makes a lot of difference. Yep. This is your acetone. This is your ethylene glycol. You have a look at this slide. The relative molecular mass is the same, but the boiling point of acetone is 56 degrees Celsius, whereas the boiling point of ethylene glycol is 197, a lot higher than your acetone. That is because on top of the dispersion forces, it also has hydrogen bonding. Yep. So in summary, in general, the strength of intermolecular forces increase in this order. Dispersion is the weakest. Dipole-dipole is the stronger than dispersion, but hydrogen bonding is stronger than dipole-dipole, and the strongest one is ion dipole. Dispersion forces operates in all molecules and depends only on molecular mass. Dipole-dipole operates on all polar molecules but compete with dispersion, and the contribution of dipole-dipole forces in polar molecule is usually smaller than dispersion forces. However, if hydrogen bond is present, it makes a significant contribution to the intermolecular interaction between the molecules. So, ada saja hydrogen bond, then you're going to have boiling point increasing significantly. So many summaries in this slide. So you're going to have, how do you compare the strength of intermolecular forces interaction? For similar weight and shape, the difference is due to polarity. The higher the polarity, the greater the intermolecular forces. For molecules that have different weight, the dispersion force will determine the strength of the intermolecular forces. The higher molecular weight will have greater intermolecular forces. So again, this is the, if you go through this slide, between interacting molecules and ions, first you ask, are there ions involved? If there are ions involved, you ask again, are there any polar molecules and ions present? If there are polar molecules and ion, then you have ion dipole. If you have polar molecules only, but if you have ion only, no polar molecule, then you have ionic bonding. So that's not covered in this discussion. But if ions are not involved, then the next question is, are there polar molecules involved? If there are no polar molecule, it's easy, dispersion forces or induced dipole. But if there are hydrogen atoms, you have hydrogen bonding. If there are no hydrogen atoms, then you have dipole-dipole forces. So that's really quite easy to understand the flow. So why is CHCl3 having low boiling point compared to CH3Br compared to CH3I? This is all because of the strength of dispersion forces that increases with the molecular size. Yep. This should be outweigh. Although chloromethane is more polar, the effect of dispersion force outweighs that of dipole-dipole forces. And again, comparing between nitric oxide with C2H6 or and ethane, you have same molecular mass, but boiling point of NO is a lot lower than your ethane, because the ethane has a greater molecular size and contact surface than NO. Thus, it has stronger dispersion force. Although NO is polar, the effect of dispersion force outweighs that of dipole-dipole forces. So there are some practice exercises. So I would like you to try this question. So far, we have discussed 4 kinds of intermolecular forces: ionic, dipole-dipole, hydrogen bonding, and London. So please determine the intermolecular forces that present in ammonia, SF6, PCl3, lithium Cl, HBr, and CO2. First, you have to look at the difference in electronegativity, and you also have to look at the difference in the molecular shape and molecular polarity. I have the answer, but later I'm going to give it to you a lot later. As another question, practice exercise number 2. For each of the following pairs, choose which substance has higher boiling point and justify your answer between pentane, which is C5H12, and 2,2-dimethylpropane, which is also C5H12. The pair of sulfur dioxide with carbon dioxide, which one will have a higher boiling point? Between ammonia and phosphine, which one will have a higher boiling point? Answer is there. I'm going to discuss with you in class. So thank you very much, everyone, for listening. This lecture is exactly 1 hour lecture. I hope you are following this lecture very well. If you have any problem, please raise your question with me, either in the group or in class when we meet you next time. Until then, take care and be safe. Assalamualaikum. And work hard. Bye-bye. Assalamualaikum.